Hello friends. So now let's solve some spring related problem. In this problem you can see that these are two rigid walls. They are not going to be moved. And the track is very much smooth. Now this block is being attached to two kinds of springs of different value of the spring constant, K1, K2. Now it's asked that if the block is being displaced by X amount towards this direction, if the block is displaced by any external force by X amount to this direction and then it is just left, you just drag it by distance X and just leave it. So what will happen? As soon as you leave it, the block will be somewhere here. So this spring would be in a compressed position by an amount X, and this spring would be in a elongated position also by an amount X. If you move this X, so there would be compression X, there would be elongation X. So what will happen? The restoring force by this spring will try to move it this way, and the restoring force by this spring will also try to move it this way, because every spring wants to get its natural position. So it's asked that when this block comes back to its mean position, at that time, what would be its velocity? So again, somewhat like previous problem, that was a vertical gravitational problem. It's a simple horizontal spring problem. Here, what are the external forces? If you consider spring as a part of system, what are the external forces? There is actually no external force if we consider a spring as a part of the system. So no external force means energy conserved. From where will it start? Our motion starts from this position, not from this position. Why? Because at this position an external force was there dragging it away by distance X. So that's a different story. Once you leave it, then it's independent of any other force. So at that time, what was the total energy? So total energy was basically your potential energy. There was no kinetic energy. The potential energy was half K1 X square in this spring, plus half K2 X square. We just can add those two potential energy terms. Now, when it will come back to its mean position, at that time potential energy will be 0, because this X will go 0. It means that the entire potential energy is being converted to kinetic energy. So we can actually replace this by kinetic energy final plus potential energy final, and this is 0, so it will be just half m v square. So we can simply cancel out this half. So v will be root under K1 plus K2 by m into x. Simple. Law of conservation of energy. V is simply root under K1 plus K2 by m into x. Now, let me ask you a very simple problem. This picture is very simple. There is an object of mass m and its velocity is v in this direction. There is no friction at the bottom of this. It's smooth. So it means its velocity will remain constant. Its speed will be constant. So it will come and touch this spring. When it will touch the spring, at that time also it will have that velocity v. So it will push the spring. So after some time, the picture will be something like this. Now, up to what distance this will move? This will push till the point its speed goes 0. And why will its speed go 0? Because as soon as it keep on pushing the spring will oppose it by a restoring force kx. This x will depend on the change in natural length. It will vary. So it will vary up to a point. Its speed becomes 0. Now as its speed became 0, what will happen the next moment? The next moment, because of the force, the spring force, this block will start moving in this direction. And it will keep on moving until the spring attains its natural length and the block just moves away. And once the block starts moving away in this direction, there is nothing to oppose it. So what will be its velocity here? Now I ask you a question, that will this velocity be the same as this, or will it be different? Now your task is first calculate it yourself, and then I will give you the solution and just match whether your result was correct or not. It's a pretty simple problem. My question is that the velocity which the block will attain after completing its path would be same as of initial velocity or not. So let's solve. When it is at this position, or say this position, what is its energy? Its energy is half mv square. No potential seen, only kinetic energy, half mv square. At this position, its energy is what? Half k x square. There is no friction. It means half mv square is equal to half k x square. So when it is back at its natural position, then again the potential energy will be 0. So this in first moment only kinetic energy, second moment only potential energy, third moment also it will be only kinetic energy. This potential energy will go 0. And what will be the value of this kinetic energy? This kinetic energy will be just equal to, at moment 3 will be just equal to the potential energy at moment 2, and that was equal to kinetic energy at moment 1. So we got half m, suppose velocity is v dash, speed is half m v dash square is equal to half k x square, and that was equal to half m v square. So from here we get v dash equals to v. Cancelling the square and rest of the terms. So what we saw? That kinetic energy is same. So cancelling the term of kinetic energies, we get v dash equals to v. It means that the magnitude of the velocity at this point and at this point is same, because here v dash is depicting speed. We are not sure about the direction, so we cannot call it as a velocity, rather it's speed. So magnitude of velocity is same at both the moments. V dash is equal to V. But whether the velocity is same? Definitely not. Velocity this direction is along plus I. Velocity this direction is minus I. So here it's V minus I. Here also it's V but I. So speed is same. Velocity is not same. That was a very pretty simple question. But I'm quite sure that most of you would have done it wrong. Just saw that, yeah, speed same, so velocity is same. Please keep in mind, IITs asks these kind of simple questions, but people make mistake because they don't look at it carefully. So please mark the words, the technical terms very carefully, what is being asked, whether velocity, whether speed, whether direction, whether magnitude of displacement or whatever. So always stick to the definition. So in this case, speed remains same, but velocity does not. Hope that's clear. Thank you.